All right, so welcome back, everyone. First off, I'm going to issue some apologies because you joined me at about 1 p.m. on Saturday. I had planned to get this out by Thursday, and well, needless to say, Thursday ended up being pretty well shot with Professor Harwood and I getting our professional headshots done. Going to Conwell's 50th anniversary expo, and then having to leave that early so that we could go over to Chapmanville to the Tug Valley Mining Institute dinner, which we attended, and so that was good. And then so Friday I'm coming back from Logan, and I get back in, open up some impromptu office hours, and now here we are. It's Saturday, but better late than never. Another reason why this video is late getting out is the presentation is considerably longer than I imagined it was going to be. Part of this is because, where I've looked at things like this for so long, sometimes I can maybe oversimplify things in my head that when I go to fully explain, it turns out it actually takes a while to explain. So this has also made me realize that I may have gone a little overboard on, particularly the pillar design requirements for the project. And so what I'm thinking about doing is, particularly since we're, already a week into the second half of the semester, probably scaling those back and only requiring the single seam analysis for the pillar design. But I do want to, to go through this with you on how you would consider these scenarios that we, originally laid out for the project. So let's jump right into it, okay? And I think that's the best way to just get our hands on this and get started. So first off, the property does look complicated, and that's because it is complicated, okay? This is a very common scenario for Central Appalachia, particularly Southern West Virginia, parts of Eastern Kentucky, all that. This is a common scenario of mines that we're trying to mine today, right? And this is also, like I said last time, based on a true story, right? I took this based on my experiences at a particular mine, and then modified that to add in a few other scenarios that we can look at for cold pillar design in multiple seam stress regimes, right? So the first thing that we would want to try to do in this is, start thinking like engineers, right? Where we're thinking of things as a system, and a system is made up of components, right? And these components interact with each other in this system, and then systems can interact with each other, right? So what we need to do is think of this as a system and then break it into its components. So the first thing we're going to do is ask ourselves if there is any way that we can simplify this problem, right? So always try to simplify first. And there is, okay? And I'll post Carl Zipp's paper on this subject, but what he concluded was that if you had an overburden interburden ratio, so that's the overburden of the primary seam that you're mining divided by the interburden to the over or underlying seam, that if it's less than 5, it can typically be excluded, right? And so we have some hilltop mining here that's 365 feet above us. I say hilltop, but it's a mid-level hill. 365 feet above us, and the overburden interburden ratio is 2.8, right? Also, given sort of the layout of this mine, how it was mined with hand loading methods, and entries were typically advanced up and then widened out quite a lot, especially like you can see. Let's get our laser up here. And especially like in this area, right? Where these were widened out past 50 feet or so. those, assuming it's mapped correctly, has caved over time, right? Over in here, it's less conspicuous, but anyways, you could also try to do some ACPS up in here and come up with pillar stability factors, but generally speaking, it's difficult to determine. Like I said, I know we talked about that before, but in this case, right, it's considerably less than 5 and can typically be excluded from the analysis, right? However, the underlying seam, right, is at a ratio of 5.5, right? So it's just barely above this cutoff. And even if it was 5 or so, I'm going to tell you now that it's going to be more important to include this seam in our design simply because it underlies the seam that we're mining, right? Influences from the caving of the underlying strata or potential instability in the pillars down there is going to be typically more important than an equal situation above you, right? And that's pretty much just because we're subsiding the ground prior to us attempting to mine. So in that case, we're going to consider this underlying seam, and you're going to see impacts from the abutment loadings in those seams, the multiple seam stresses. You will see impacts from those, okay? And I'll show you where you might encounter those as we go along, and yeah. But so, now we're down to 2 seams, right? We're down to the seam that we want to mine and the seam underneath us. So always simplify the problem if it's possible. Now, what we're going to look at is, what is the state of stability of the pillars in the lower seam? And we started looking into this with ACPS examples a few weeks ago, but now we're going to get right into every scenario that was, initially discussed in the project, that sort of thing, and go from there, right? And so the first thing we're going to look at is what is the depth of cover for each of these panels, right? And we noticed that these were all mined on 80 by 120 foot centers with what appeared, to be modern mining techniques, right? So you could even assume that your company mined this, right? It's possible. And there are 4 individual scenarios here. So there's no undermining, development only, full extraction, and partial extraction with splitting pillars, right? And because we have this 1,000 foot ridge that just sort of runs through here, pretty much our depths of cover for all the panels are the same, right? 1,000 feet to the active seam plus 180 feet to the underlying seam, with the exception of 3 right, which because of this big flat area here, it looks like there could be a small area that's 1,100 feet of cover or so, right? So I increased that to be sort of an average and weighted a little bit towards the high end or sort of the low end, I'm sorry, because between 1050 and 1100, right? So that's what I'm going to use for this, 1,250 feet to the lower seam. And so we're going to need ACPS to calculate the stability, and we're going to start with the underlying mains, right? That's where we're going to start because that's where we're going to put our set of mains. It would stack right over top of these, right? That's where you would lay it out and just stack your pillars. And it'll be a little bit conservative compared to this calculation because of the extra 180 feet of overburden, but it doesn't matter. This is dictated to you by the conditions that you are, mining into. And so with this, we click results and we see that our stability factor of the underlying mains appears to be quite stable, giving the 1.5 stability factor. Design criteria, it's obvious that these pillars were sized for long-term stability, right? Long-term stability and are, most likely, fully intact, right? And then we can do this for the one right panel too, if we wish, by just adding in, same pillar size, right? Same depth. And we're going to add in a retreat section because the 2 right panel has been retreated, right? And we add that in, one side gob, there it is, and the barrier pillar width. And when we click results on that, we see that those pillars are definitely stable, pretty much the same as being in the mains, except for there is a little bit of loading that's coming across the barrier, which our barrier pillar stability factor is 2.0, and that's good, right? That's it's above the 1.5. It's a very nice, strong barrier. So that's what they left behind. And what about 2 right? Right? That's funny. So T right U being underlying panel, right? The second right underlying panel. There, there's an active retreat section, right? But there's no side gob there like there was in the previous scenario because, nothing else was mined around it. So, and this also takes into account for 1 right, because we put the side gob in. That takes into account the additional stress from mining this panel, based on like the order they were mined in, right? So, we have this scenario for 2 right, and we get retreat stability factor of 1.68, which is higher than 1.5. We did not necessarily consider the stability of the barrier in this analysis, and that's because we considered it in the previous one, right? We looked at the barrier. Barrier had a 2.0 safety stability factor on it, so we've already included it. Now the monkey wrench, and that's the 3 right U panel, right? So here we go. We've increased our depth of cover slightly to 1,250 feet, right? And to show that these pillars were like split, basically you can think of them because they're fairly large, and if you would just take like a little Christmas tree slice out of the middle of each one, even though they're at an angle, you could consider that basically the crosscuts were cut in half, right? And so what I did was I decreased the crosscut spacing to 60 from 120. And when you look at the retreat from the 2 right side gob, right? So the 2 right's been retreated. We have to add that in, right? So there's no active gob, but there is 560 feet of gob beside of us and a barrier that's 100 feet, right? And when you look at that, the results are undecided, right? Our stability factor is less than 1.5, which would, indicate, a 90% chance, roughly speaking, of success, right? But we're below that. But we're not all the way down to a 1, which, would theoretically be, the least stable value, right? Right at a 1, like it's just barely standing there. But we're above that, right? So there is a chance that these pillars are currently stable, and there's a chance that they are not stable, right? We're not sure. So now the active seam. We've determined the state of stability for most of the underlying seam. And what about the active seam? So for the first panel, 1 right off of this 1 west mains, we've got about 850 feet of space to consider, right? And we need to consider the barriers. So the first thing you want to think about is how much size barrier do I need off my north mains to make sure those stay stable? And for that, I would consider first the empirically suggested abutment extent. What is that? How far does the load transfer when I pull all those pillars out of 1 right? And 90% of the abutment load is distributed within a distance of 5 times the square root of the depth, right? So if we take 5 times the square root of the depth, which over in that area is about 800 feet, we get 141 feet as the abutment extent. Okay, cool. So 90% of the load is dissipated there. So that's a general guideline for us to go by. And we also need to consider the stability of the north mains after we retreat mine the one right panel, right? So we need to consider that. And we can use ACPS again, right? We put in our active seam parameters, okay? In this case, I used 1,000 feet of cover in the analysis just to make sure we're getting the highest, stress in that that's going to be seen on that panel. And then we'll add in our retreat mining parameters, with our 560 feet of side gob there, and 100-foot barrier. And I chose that simply because that's what was underneath me, and it seemed like it would work down there. So let's see what that looks like here. And the results do suggest that if you want to keep a 2.0 on that barrier between the mains, you could take it down to a 1.5, right? But at a 100-foot barrier, you're sitting at a 2.0 roughly. 2.0 on the stability factor in the mains as well, given the abutment extent being 141 feet, given that the roof and overburden is fairly stiff in Central Appalachia, and it may go somewhat further than that, I would probably recommend stopping here and not cutting it down to 70 feet or whatever. And so if we leave that 100-foot barrier, and then we assume that there's probably going to have to be another one on the other side, between one right and two right, we're down to about 630 feet or 650 feet of space. When we're looking at entry centers, we could have 8 entries up to 80-foot centers, or 9 entries of 70-foot centers, right? Those would all fit in there. So let's check ACPS, right? Let's see what 70 by 120 feet looks like. And when we add in our retreat mining parameters for the first panel, right, it's just the active section. That's all we've got. And we see that our retreat stability factor is a 1.32, and it doesn't work, right? But you could use 7 entries though, instead of 8 or 9. And it would work, right? So by narrowing that down, the panel width, you've reduced the stress on the AMC, right? So stress on the panel until you get to a supercritical width, until your width is equal to or greater than the overburden depth, you'll see an increase in stress based on the square of the panel width, right? So that means your stress increases actually fairly rapidly as that panel width increases, because it's the square. So you could use 7 entries. You could probably get by if you wanted to run a continuous haulage system, right? And run smaller centers like 50-foot centers. You could probably get by with that. And it turns out you'd be right on the cutoff, right? So, I mean, maybe if you could tweak that just a little bit. It's basically the angle of the pillars that slightly decreases that below a 1.5, and you could run a system like that if you wanted to. The largest pillars that you can kind of fully Christmas tree. So if you're taking cuts, from both sides, and you can get in about maybe 35 feet tops, right? But you're at a little bit of an angle. 80-foot centers is roughly the widest pillar that you can Christmas tree from both sides and actually get all the coal. You can get a little bit wider than that, say 85 feet, and you can leave a little bit of coal in the middle that would generally, crush out relatively easily. But to get it all, this is kind of as big as you can get, and that's probably what you'd end up going with, right? You end up with a 1.5. It is doable, and that is if you, when you're looking at the retreat mining, this is probably it. And you could mine rib to rib with this, although it just depends on what district you're in. what they'll allow and disallow. Some areas you might be able to take a slab cut out of the barrier, some you may not. Some you'll have to leave half a leaf block at least, for ventilation purposes. Some you can mine rib to rib, right? So it just depends. But in this case, you could mine rib to rib with this layout, and have a 1.5 stability factor. But does this also work for the 2-right panel? So for that, we need to take into account our active gob in 2-right plus the side gob in 1-right. So when we do that, it does work for the retreat analysis. We still have a good above a 1.5 stability factor. Our barriers are still very stable, well above a 1.5. So it works for the retreat analysis. But remember, there's pillars underneath us too. And so, does the retreat mining impact the stability of the underlying seam? And when we switch it around, we'll consider our underlying seam as the primary seam with our input parameters, and then we'll put, if you click the CMRR estimator, Central Lab, especially in this area where this mine takes place in, relatively high CMRRs. We had very strong roof. So the roof's strong. So you get a CMRR that's probably about 50, maybe 55, something like that. Okay, that's so not super, not 80, right, and also not 40. So put those in. Our inner burden thickness, 180 feet, and we're the active is under the previous, right? Because we're thinking of this as if we were in the lower seam, right? And we have this gob solid layout, our 560 feet of gob, and it turns out that it still appears stable as we retreat mine over top of those pillars, right? So we're going to retreat mine over the top of those pillars, but it is unlikely that they fail, and an interaction from the multiple seam conditions, we get a green. Let's get this laser pointer back on. I don't know what happened to it. We get a green, so major interaction is unlikely, right? So that's good. So now we've got 1-right and 2-right finished. Well, what about 3-right? 3-right's a little bit different, right? We're going to be mining up underneath this gob area right here. And as you'll learn in next semester's ground control class, the areas around these gobs have high abutment loading, which turns into high multiple seam stress, so that when you try to mine through them, you get elevated stress, conditions become difficult, rib spalling occurs, roof and floor problems can occur, okay, and all of that. So that's where the high stress is, but then once you get under the gob, generally speaking, it's relatively de-stressed, right? At least from a vertical stress perspective, there's a de-stressing here. However, there is also, like I said, subsidence over that area. So roof support is going to become a larger concern in these regions, right? So you'll have high stress crossing into the gob, and then a de-stressing followed by, most likely, fractured roof material. Okay. So with that, generally speaking, we would not want to stack our pillars here because of the way this was mined. This is a slab cut taken off the left barrier and half a block left on the right. Okay. So we, generally speaking, would not want to drive an 1/8 entry through here, and instead would stay under the gob with roughly 7 entries here, right? 7, not roughly, but definitely 7 entries here. Although you could, because of the nature of, this more modern mining, it's assumed that what you actually did retreat mine out of here. You could use different layouts. It doesn't necessarily have to be like this once full extraction occurs, right? But you need to be sure that it did. Otherwise, I would consider this stacking, just in case there's a pillar that was left in there or something like that. And so back to ACPS we go. We have our 7.5 foot or 7.3 foot entry height. Our depth of cover, right, is a little bit less because I'm looking at this as exactly where we cross the gob at, right? So I'm looking at the average overburden depth within 200 feet of that location, right? So it's a little bit less. Our entry width is 20 feet. Our standard 80 by 120 crosscut pillar spacing. You could even bump this down to 100 if you wanted to. It'll probably work. I don't remember. Let's double check. But we also need to take into account our retreat parameters, right? So we have our active gob and then our side gob, which is 560 feet, except because of the way we're dropping that one entry, our barrier is substantially wider now. It's 190 feet. Okay, so now we can add in our multiple seam parameters. Once again, a relatively high mid-level, 50, 55 CMRR for this particular case. Inner burden thickness 180. That lower seam was 6 feet thick, remember, and that gob width is 560, right? And this is a gob solid layout rather than a remnant structure. Okay, so it's you'll be crossing a relatively wide gob area. The remnant structure, such as a barrier with gob on both sides, or just a remnant pillar in and amongst a bunch of gob, that's going to be much more highly loaded than the gob solid crossing, right? So this is actually more favorable. So we put those in, and our active is over top of the previous, remember, so there's undermining beneath us, and the results we get are this, right? So on retreat, our stability factor is 1.49. Now, they may or may not, round that and approve it, but this assumes that we retreat mine all the way back to the gob edge, right? And so I'll show you in a minute what you might do instead, okay? As far as ground stability, on development, it's predicted to be green, yet on retreat, it's predicted to be yellow, okay? Yellow means that, a major interaction could be likely, unless, a pattern of supplemental supports installed. Most likely, especially because this is overmining, so you may need to install this for the entire length of the panel, because even though you're not in this highly stressed of an area, you are in potentially broken ground, so it's likely that you will need supplemental support, or typically cables installed throughout the panel. So like I said, it assumes that we're mining right up to this gob edge. So we're extracting all of these pillars back until you have these two leave rows, which provide, a bit of a barrier, to the mains here. Okay. And remember that our stability factor was 1.49, and it's just, like I said, right on that cutoff. But if you stopped mining here instead of here and left a third row of leaf pillars, that would become a moot point, because you'll no longer be retreat mining all the way up to this edge where you're putting the most possible stress onto these two rows of pillars, right? Stop a row shy and everything up in here is de-stressed, including the majority of these pillars here too, right? So that would, by default, sort of increase that stability factor if you did not take the last row. All right, so we've got panel 3. One last thing, I did put this sort of ellipse here, which would indicate, areas that would absolutely need supplemental support, right? Either from the high abutment stress and therefore multiple seam stress in this area, right? So you're getting abutment and multiple seam stresses in here. You're going to need supplemental support in here. And then as you cross over the gob, you'll see bending, right? You'll see bending of the strata, you'll see fractures, and then eventually that will sort of level out, right? So definitely supplemental support in these areas. 7.3 foot, mining height is what we're putting in here. It's actually higher than that because we took a discount for the rock. You're definitely going to need rib support in these areas as well, okay? And most likely due to the depth of cover, you're going to need it throughout the mine. Mostly anything over 700 feet of cover or an equivalent stress level, based on modeling. That sort of thing is going to dictate your rib support for now until we get better software tools out there. But this area for sure, and then probably the entire panel as well. Okay. So what about foreright? Foreright, if you remember, is the monkey wrench. Okay, foreright, where those pillars were split underneath us, resulted in an indeterminate sort of stability, right? There is a significant chance that if you retreat mined over those pillars, where they're already in this sort of state of potential failure or near failure or that sort of thing, the additional, multiple seam loading from extracting pillars over top of it, right? So you get this abutment loading on the at the pillar line, right? That gets transferred to that lower seam. It puts more stress on those pillars. Chances are they will move more, okay? How much that impacts the seam that you're in, it's hard to tell, right? There are many scenarios where places have mined over pillars like this successfully, but there are also cases of failure, okay? So most likely, and we're going to go back to ACPS one more time to look at this, right? We can, if we decide to do like a leave row like we were going to do, in the other panels, put in our active and side gob parameters, considering that the side gob's a bit narrower this time because we only had 7 entries in 3 right. And also put in some 19-foot wide entries here. ACPS suggests that it's stable, right? Okay. 1.5, stability factor and retreat. So if you could get in there and keep those entries at 19 feet, which is possible, okay, I know it would be complained about, but I've seen it done. You could get what appears to be a stable, system, but is it? And I'm just going to tell you the answer. You can put this in ACPS if you want and do the multiple seam analysis. Sure, it will reduce the safety factor. It's going to tell you that those pillars are not going to be stable long term, and the answer is that when you start retreat mining this panel, you need to be prepared. Well, obviously on advance, right? You need to start monitoring this on advance as you're developing, looking at the conditions, because there could be indications that the pillars below you have already failed. If you're seeing a lot of fracturing in the roof, if you measured, maybe even the subsidence in there, right, when you're surveying. When you're surveying it, do you see a trend that looks like that subsided? Then you can start making the conclusions that, yes, these pillars have already failed. Let's go ahead and retreat mine over top of them. As you develop, you may not run into any problems, and you may get all the way to the back and get ready to start pulling pillars. You do, and then eventually you start loading those pillars up underneath you, and they'll fail sort of progressively. They'll fail a while, and then they'll stop. And then you can sometimes, if you keep mining, catch back up and start the process over again. And it's sort of cyclical, right? It happens sometimes. So basically the answer is what you're going to do is you're going to assume that things are going to work out. You're going to lay out that panel just like you would any other. Stack the pillars, advance it, monitor it as you go, start retreat mining, but be prepared to abandon that panel at basically a moment's notice. Keep it in mind, you may have to pull out of there, okay? And so that's the moral of the story. We've made it to the end. I know that was long, and there was a lot in there to digest. So once again, this is how you would approach the thought process behind it and the systems that sort of control, pillar stability in a three-dimensional multi-seam stress field, okay? That's what we looked at, and we looked at basically some of the more complicated scenarios that you can run into that are solvable with the ACPS, right? And then not necessarily like what you see on this image here, which needed some numerical modeling analysis and that sort of thing. So with that, this is how you approach, what was originally put into the project. I think with the time remaining in the semester and, this whole concept of building this, rocket ship while we're flying it is, pointing us in the direction of this is probably a little bit too complicated for the project, and that what we need to do is instead just consider a single seam analysis and focus a little bit less on my favorite subject, pillar design, and a little bit more on some of the other aspects of equipment selection and that sort of thing, and we need to do roof support too, right? We need to talk about rib support, all that. So that given the length of what this took, I'm thinking that's maybe a little excessive. So, but here it is. It's out there. We can refer back to this in the ground control class as well, right? Because I'm basically giving you the keys to the car right now, and next semester we're talking about what's under the hood. Okay, so that's when the fun's really going to begin. When it comes to ground control, and instead, yeah. So with that, I'll catch you next time with another sort of video lecture on what the next steps on how to approach the project, and we're going to continue this over the next couple of weeks until we've basically walked step by step through both of these projects for this class and the surface class as well. So with that, thank you, and we'll see you next time.